Hello, welcome to all. In the previous lecture, we studied the electromagnetic wave equation for the free space. Okay, and also we studied the nature of electromagnetic waves, particularly the transverse nature of electromagnetic waves. Okay, now let us see the outline of today's lecture. Now, let us derive the electromagnetic wave equation in a dielectric medium. Okay, then we will get the velocity of light in that medium. After that, let us write down the equation for the energy density of the electromagnetic field. Why? Because we know the energy densities of electric field as well as magnetic field. Next, finally, let us do the Poynting theorem. Okay, right. Now, let us go for the first topic of our today's lecture. To derive the wave equation in a dielectric medium, we have to consider the Maxwell's equations for the dielectric medium. Okay, Maxwell's equations for the dielectric. Okay. What are those equations? I will write here. Del dot D is equal to rho, del dot B is equal to 0, del cross E is equal to minus dou B by dou T. Okay, why? Because in these two equations we have neither charges or nor currents. That's why there will not be any change in these two equations. So next, the last one is del cross H is equal to del cross H is equal to dou D by dou T, dou D by dou T. Okay, so if you take the linear dielectric medium, you have now here this del dot D as del dot epsilon E is equal to rho. So you have this as del dot E is equal to rho by epsilon. Okay, first one. There is no. Next, let us go for the last equation. Here, for the linear dielectric medium, you have this D is equal to epsilon E, and here H is equal to B by mu. Okay, so here you have del cross B by mu on this side dou by dou T of what is this epsilon or epsilon E. Okay, here you have del cross B is equal to, now if you take this mu to this side, mu epsilon dou E by dou T. Now let us write the Maxwell's equations for a dielectric medium with the same physical quantities. Okay, what are those physical quantities? E and B with the dot product and cross product. Okay, here before this we had here one D and one E, one B and one H. Okay, so now what we have done is we transformed these equations into only two physical quantities. Yeah, then what are the transformed equations? What are the final equations? Now, therefore, I will write here, this is transformed to which equation here? Del dot E is equal to rho by epsilon. It represents the medium. Okay. Next, last equation. We modified the last equation now. Here, it reduces to del cross B is equal to mu epsilon dou E by dou T. So now these are our Maxwell's equations for linear dielectric medium. By using these equations, now we are going to derive the wave equation. Let's take curl on both sides of equation 3. Taking curl on both sides of equation 3. Yeah, the derivation goes on very similar lines of the derivation of a wave equation for free space. Okay, del cross E is equal to minus of dou by dou T of del cross B. Del cross B. Yeah, here A cross B cross C, use back cab rule. A cross B cross C. Here B. Okay, A dot C minus of C, A dot B, AB. Okay, this is equal to minus of dou by dou T of del cross B. Okay, here you substitute now for both del cross B and del dot E in this equation. Okay, using equations 1 and 4, we have how much you are having here. I am writing here now. Okay, I am writing here. Yeah, this is 0 anyway. So del into 0 minus this is del square E is equal to, on this side, right from the fourth equation, write del cross B is equal to mu epsilon dou E by dou T. Okay, minus dou by dou T of mu epsilon dou E by dou T. Okay, so now you have minus, this is 0, del square E is equal to minus mu epsilon dou by dou T of dou E by dou T, means dou square E by dou T square, minus minus cancel. So now you have the wave equation for E. What is this? You write epsilon mu epsilon dou square E by dou T square. You see what is the difference between this equation and our previously derived equation? There you have mu naught epsilon naught, that refers to free space, this refers to particular material medium. That is what the difference. Yeah, entire procedure of derivation is same, equation is also looks very same, except in the place of mu naught you have mu, in the place of epsilon naught you have epsilon. This is the wave equation for E. Okay, now if you start from this fourth equation, then you have the wave equation for B. Okay, now yeah, I will modify here, taking curl on both sides of equation number 4 now. Okay, right, here you have del cross B. Now here on this side you have what you are having, mu epsilon mu epsilon dou del cross E by dou T. I am multiplying with del cross here on both sides, here also taking curl on both sides of this equation, fourth equation. Now we have to change this to be B. Here also we have to change this to be B. Okay, on this side what you are having now, instead of this, here mu epsilon, here del cross E, dou by dou T of del cross E. Now you are using equations 2 and 3. Equations here is 2 and 3. 2 and 3. See, by using these two equations, you will get 0 this way, because this is also 0. Here this is del square B instead. Okay, on this side what you are having? Mu epsilon. On this side what you are having? Mu epsilon dou by dou t of, what is this? On this side, mu epsilon, this is okay, dou by dou t of del cross E now. Then what is that? Minus of dou B by dou t. Okay. Now, this is anyway 0. Here you have del square B. Okay. Here also you have minus mu epsilon dou square. Here this is instead of E, you have to write B. Minus minus cancel. You have here del square B is equal to mu epsilon dou square B by dou t square. Okay. We followed the similar procedure. Okay. But we started with fourth equation. We took curl on both sides of this fourth equation and we substituted this second and third equations now. Okay, we substituted the values of del dot B and del cross E from second and third equations. Then we get the wave equation. Okay. Then we got the wave equation for B as this equation. See, what is the difference between this equation and previous equation? Only the letter. In the place of E now we are getting B. So E and B are following the same wave equations. So you have similar solutions for D as well as E. Okay. So what is the general equation? Electromagnetic waves. So you may write the general equation del square is equal to mu epsilon, okay, dou square by dou t square dash, means here in this dash you may put either E or B, okay, either E or B, right. This is the general equation for electromagnetic waves in material medium, linear dielectric medium. So here, what is C square now here? What is C here, or 1 by C square? From this equation, this is in the standard form. This is in the standard form. Okay. What is the standard form? Dou square, say some y is equal to 1 by v square, dou square y by dou t square. So in the place of 1 by v square, you are having mu epsilon. Okay. Okay, I am erasing this now. Okay. Standard form. So in the place of 1 by v square, you have now mu epsilon. So your v will be now mu epsilon. Okay, this is not constant. Okay, it depends on the dielectric medium. Previously we had this as C, that is equal to 1 by mu naught epsilon naught. That is what the difference between electromagnetic waves in the free space and electromagnetic waves in the medium. Okay, in the medium, right. See here, the velocity of electromagnetic waves in material medium is different from that of the velocity of electromagnetic waves in vacuum or free space vacuum. Okay, right, that we have to note. Okay, right, this is about the electromagnetic waves in a linear dielectric medium and their velocity of electromagnetic waves in the material medium, right. Yeah. Now It depends on the given dielectric, linear dielectric medium, given dielectric medium. Okay, right. Next, let us go for our next topic. Velocity of light in medium is also over. This is the velocity of electromagnetic waves in the medium. Okay. Next, topic is energy density of electromagnetic waves. This you can readily write this thing. Why? Because in the previous chapters you already studied the energy density in the electric field as well as energy density in the magnetic field. Okay. Now let us deal with the energy density of electromagnetic energy density of electromagnetic field. Okay, what is the energy density of the EM field? Electromagnetic means you are having two fields simultaneously at one place. Okay, the space is filled with both electric field as well as magnetic field whenever the electromagnetic waves propagate through that space. So energy of electromagnetic field is equal to energy of the electric field, or it may be energy or energy density. Okay, energy density of electromagnetic field is equal to energy density of electric field plus energy density of magnetic field. Okay, energy density of electric field plus energy density of the magnetic field. This will give you the energy density of the electromagnetic field. You know this. What is this? Otherwise, this is U, E. This is our notation. U, B. Okay. This is simply now U, EM. Okay. Right. U or U electromagnetic EM, or simply U is equal to UE plus UB. Energy density of the electric field plus energy density of the magnetic field. Okay. Now you know that this is half of epsilon naught. Let us take this for the free space only. Okay. The vacuum epsilon naught E square. Okay, plus half, otherwise 1 by 2 mu naught B square. You know this. Okay, we derived these equations in the respective units. Now if you want to write in exactly the same form, here you have to replace B with mu. Okay, here what is, otherwise you write here, I will write here now, otherwise so U is equal to, what is this, half epsilon naught E square plus 1 by 2, here you are having mu naught, na? You multiply with mu naught here, otherwise you write mu naught both in the numerator and denominator. Then what happens? Half mu naught, this is B square you are having, here you get mu naught square, na? So you write mu naught, just write whole square. Okay, this is equal to half epsilon naught E square plus half of mu naught. What is this B by mu? Is a h. B is equal to mu 0 mu naught h. Okay, so What is this now? H E square plus. Now this term and this term look very much similar. Okay, so we use this final form for the energy density of the because why we are writing like this. Okay, B is equal to mu naught H, or H is equal to B by mu naught. Okay, this is our final expression for the energy density of the electromagnetic fields. Why we are writing this equation? Why? Because this will help us to study the Poynting theorem. Poynting's theorem. Next we will go for the Poynting's theorem of electrodynamics. Poynting's theorem. Okay, yeah, this is final topic of this unit. Poynting theorem. Yeah, this was derived for the first time by the Poynting. That's why we call this as a Poynting theorem. Okay, in the early part of 19th century, he derived for the first time a theorem known as a Poynting theorem. Okay, yeah, what is this theorem? Whenever you want to write the Poynting theorem, you write one word as Poynting vector. A vector associated with this theorem is known as Poynting vector. It is simply the cross product of our two quantities E and H. E and H. Okay. What actually the Poynting theorem says? What is the definition of this thing? See, energy laws in particular volume in electromagnetic field, or electromagnetic energy laws, is equal to the work done, okay, on the charges in the system, okay, per unit time plus the net flow passing through that surface per unit time. It is nothing but another form of law of conservation of energy. Otherwise, it is the law of conservation of energy for the electrodynamics. Okay? Electrodynamics. Simply again, we consider the case of vacuum. Okay, and also we assume that there are no free charges and currents. In that case, okay, this Poynting theorem, equation of this Poynting theorem will be like this. Say this as a d w, or whatever it may be, d u by dt, loss in the energy, electrical energy from the volume, is equal to the electrical work done. See, this work is done, okay, whenever there are some free charges. We are not having free charges, so the electrical work is 0. Next, what's the other term we are having? Net flux. Okay, net flux. This is given by the divergence, okay, of say some vector called as S, total net flux divergence, del dot S. This is a mathematical equation for the Poynting's theorem. Poynting's theorem under the conditions we assumed so far. Okay, we are assuming the free charges or free currents to be 0, and we are taking the case of the vacuum. Then you have just dou u by dou t is equal to minus dou u by dou t is equal to del dot S. Here S is known as Poynting vector. This is a vector product where S is equal to E cross H is the Poynting vector. Poynting vector. S is a Poynting vector. Now we will see that S is equal to E cross H. We prove that S is equal to E cross H. Okay. For that, so we start from this derivation, okay, and we will prove that this S is nothing but E cross H, right? Now let us start from now. What is our purpose? See what is the physical meaning of Poynting vector S, or you may call this as a P also. You may call this as Poynting, no? So you write P, no problem, P, but it is not the polarization vector. Okay. Now here it is the Poynting vector. Okay. Right. Otherwise you simply put yes. Right. See, what is the physical meaning of this Poynting vector? It will gives you the rate of otherwise energy coming out of the electromagnetic waves through unit area per unit time. You take some unit area in the electromagnetic field and you just observe that how much energy is coming out of that surface per unit time. That will give you the magnitude of Poynting vector. Then what will be the direction of this Poynting vector? It is a cross product of E and H. You may use a right hand rule. Okay, you may use the right hand rule, or you may simply come to the conclusion that P will not lie in the plane in which E and H vectors are laying. That means the direction of P is nothing but the direction of propagation of the electromagnetic waves. Okay. Yeah, in this way, Poynting vector gives us the direction and magnitude. Okay, Poynting vector's direction is perpendicular to that surface which you are considering. Okay, right. Now what is the physical meaning of this Poynting vector? It will gives you the energy loss per unit area per unit time. Unit area per unit time. It will give the magnitude of energy passing out from the unit surface per unit time. Okay, right. And it will be perpendicular to that surface. Okay, through which you are observing the energy dissipation. Okay. And this direction of this Poynting vector is perpendicular to the plane of E and H vector. You know E and H or E and B are perpendicular. Then it will be again perpendicular to this plane of E and B. Okay. Now let us prove that this P is equal to E cross H from this relation. Yeah, this is a loss in that particular surface, loss of electromagnetic energy. This is a flow of electromagnetic energy coming out of that surface. So whatever that loss is there, Okay, that loss is equal to the whatever the loss you have inside that surface, that is due to the flux from that surface. Okay, that's why we call this as another form of law of conservation of energy, or law of conservation of energy of electrodynamics. Okay, now let us prove this. P is equal to E cross H. Right. For that, let us start with this equation. Okay. Now, what is U? Here, you may write this in integral form as well. For that, what you have to do? Yeah, you have to take some volume integral. Then on both sides, you may take volume integral. Yeah. Or okay. Take volume integral minus dou u by dou t dv is equal to volume integral del dot p div p dv. Okay, div p dv. You may write like this. Okay. Here you may convert this into a surface integral if you want. You may convert this into the surface integral. Okay. Right. Now, what is U? I will write here. Okay. We have U is equal to, just now we wrote down this thing, half of epsilon naught E square plus half of mu naught H square. Let us try to find dou u by dou t initially. What will be this dou u by dou t? Can you guess this? This is okay, half of epsilon naught. This is 2e. Okay, into 2e. Okay, 2e dou e by dou t. Okay, plus half of mu naught. What is the time derivative of this h square? 2h dou h by dou t. Right? Now this 2 and this 2, this 2 and this 2 cancel. You have this is equal to epsilon naught E into, now you write this dot dou E by dou t plus, okay, mu naught H dou H by dou t, dou H by dou t. Now, we have expressions for dou E by dou t as well as dou H by dou t in the Maxwell's equations. In order to substitute these two values, now we have to go for Maxwell's equations. Using Maxwell's equations, what you are having here, what is your dou E by dou t? What is your dou E by dou t? Was there a difference you are having here instead of yeah? What is dou E by dou t? Yeah, we are taking the Maxwell equations for the free space only, no problem. See, this is dou E by dou t is equal, which Maxwell's equation you have to consider? Lost Maxwell's equation. Okay. What is this actually? This is E. This is you see, using Maxwell's equations here, what is dou E by dou T? That is 1 by mu naught epsilon naught into del cross B, into, otherwise you write here del cross B by this thing, okay, using third Maxwell's equation, plus, otherwise I will write here only, plus mu naught H. What is this dou H by dou T? Actually, you have for dou B by dou T. Yeah, this is, here you are using which Maxwell's equation? Fourth one. Here you have to use third Maxwell's equation, that you have to note, right? Yeah, this is, you get this d by dt in the fourth, last corrected Ampere's equation. Now you get dou H by dou T in Faraday's law, third Maxwell's equation, but that will be there in the form of dou B by dou T. So this is just, I will write this as 1 by mu naught. Then what happens? When you write this mu naught here and also here, then you get B there, dou B by dou T. Okay, now let me write this dou B by dou T from the fourth Maxwell's equation. This is equal to epsilon naught E, okay, dot del cross B by mu naught epsilon naught plus mu naught H, okay, 1 by mu naught. What is dou B by dou T? It is nothing but del cross E, del cross E, okay. Yeah, now you cancel this thing and this thing, you have, okay, 1 by mu naught E dot del cross B, okay. Anywhere you have minus, here this is Faraday's law, no? That's why here you have, how much you are having here? Minus of del cross, that's why you write here minus. So here you get, okay, this mu naught cancel, yeah, is it correct here? Mu naught H square, you are having 1 mu naught H, okay, see, I am writing this H as again mu naught B by mu naught, okay. So dou B by dou T is again your del cross E, okay, right. But here minus into plus minus, you have, okay, some H into, okay, del cross E, no? Okay. Now you write this H also as B. Why? Because we are writing one H in terms of B. You write this H also in terms of B. Then you have E dot del cross B, okay, minus, what is this H? H is equal to B by mu naught. So you write this as 1 by mu naught, you write outside. Now this is B, okay, B dot del cross E. So now you have 1 by mu naught common. Inside the brackets you have E dot del cross B minus of B dot del cross E. Yeah. Now we are using the vector identities here, del dot A cross B. Okay, we are using del dot A cross B relation. Here you have, in the place of A and B, you have this E and B. Okay, here these are the general vectors. Here B is a magnetic field. Okay, right. Then you see B dot del cross A minus A dot del cross B using this relation. Okay, here what you are having here, you want to write this for E cross B. Okay, this is equal to, okay, I will write here, otherwise here the space is over, na? Yeah, right. Now we will write this for del dot E cross B. Now you apply the same identity here. B del cross A means here also you have B del cross E minus A del cross B means in the place of A you have E vector here, del cross B now here. Okay, right, use this identity. But here what two terms you are having? E dot del cross B minus B dot del cross E. Okay, E dot del cross B minus, okay, same terms, but here you are having minus, here you are having plus. So what is this? Therefore this is equal to, what is this? Dou U by dou T, na? Is equal to, okay, you compare this thing here. Actually for this term here you are having plus and this for this term minus. That means if you multiply this formula on both sides with minus, then you have these two terms as a RHS and minus del dot E cross B as a LHS. So instead of this you may replace minus of del dot E cross B. Okay. Yeah, so minus of dou U by dou T, if you want minus of dou U by dou T, that will be simply del dot, okay, E cross B, del dot E cross B. Okay, right, but we have minus dou U by dou T is equal to how much we are having? Divergence of some Poynting vector. So Poynting vector. So you just compare these equations. Therefore, in the place, what is P now by comparing these two equations? P is simply E cross B. Yeah, so we proved that Poynting vector is nothing but the cross product of E and what's this? And here you are forgetting something here, na? By mu naught is here, na? Yeah, here by mu naught you write this by mu naught. Okay, here del dot in the place of P, what you are having now? By mu naught. Okay. If you want to express this in terms of H, then what you are having here? P is equal to E cross, what is B by mu naught? This is nothing but H. So we proved that our Poynting vector is a cross product of E and H vectors. This is what the Poynting theorem. Okay, and its associated vector. We proved that Poynting vector is nothing but E cross H. E cross H, right? So what is actually the Poynting vector? This will give you the energy rate per unit area. Okay, energy rate per unit area, right? Yeah, it is a very simple way of getting this. Okay. Yeah, let us stop with this. Thank you.